So hello everyone, today we'll be understanding the concept of greedy normalization. It's very basic, classical, I would say classical minimization problems can be done using this. So what is it? It works on a simple uh, analogy kind of thing. Let's say this is you, this is you, and this is your friend. All right, this is you and this is your friend, and this is the distance between you and your friend. All right, this is the distance between you and your friend. And let's say your friend is sort of lazy. All right, let's say your friend is lazy. The question is how much minimum energy, how much minimum energy you should be spending to reach your friend. All right, this is some distance between you and your friend is lazy. What's the minimum energy you should spend to reach your friend? This is one case. This is, let's say, case 1. Let's number it as 1. Case 2 is you are lazy. You are lazy. All right. You are lazy. So how much your friend should spend to reach you? All right. This is it. And if both are normal, let's say both are not lazy. Let's say both are not lazy. Case 3 is both are not lazy. In that case, what would happen? You would walk half distance. He would walk half distance, and both of you would meet so that you spend the minimum energy. All right, so that you would spend the minimum energy, or to minimize both energies, equally minimize both energies. So you would meet at the midpoint. In the very first case where your friend was lazy, you had to walk the whole distance. In other case where you were lazy, your friend had to walk the whole distance. Is this clear? When one of them is lazy, the other walks the whole distance. When uh, let's say both are not lazy, both of them walk half distance so that they spend the minimum energy. Fine. I hope this analogy part is clear. Based on this only, we'll be solving the problem such as minimum number of moves to make array elements equal. And let's say this has three cases. In the first case, you can only increment. You can only increment values. In second case, you can only decrement values. And in third case, you can do both. Say this is the problem. Like we need to solve three cases separately. Let's pick the first problem. Let's pick the first problem. You can only increment. Let's say you have some array 1, 2, 3. And you can only increment stuff. You can only increment stuff. You cannot decrement anything. Fine. Now, uh, how to find which is an optimal move? Which is an optimal move? If you have this maximum element, if you have this maximum element, uh, you can increase this to the maximum element. You can increase this to the maximum element. But if you increment the maximum element itself, the arrays like the total what can I say, balance of the array would shift towards the maximum, right? If you increment something, You need to make this array balanced. So if I increment this, let's say the balance for now is something like, this is disbalance, however. If I increase this, the balance would get even worse. All right. I'm increasing the maximum element. That means if I sketch a graph here, 1, 2, 3. This is the condition. If I further increase this, this thing would get more steeper. This thing would get more steeper. All right. That means I shouldn't be increasing the maximum element. I shouldn't be incrementing the maximum element. It would cost me more moves. Okay. It's like, let's call this direction as incrementing, this direction as decrementing. All right. It's like, this is the initial distance between you and your friend. If I'm moving your friend further this way, the distance would increase, right? The distance got increased here. All right. The distance got increased. So to avoid this, we don't increase the maximum element. Now, since you're not increasing the maximum element and you can only increase stuff, that means you cannot perform any operation on the maximum element. Is that clear? You cannot perform any operation on the maximum element. All right, you cannot perform any operation on the maximum element. Now, since you cannot perform any operation on the maximum element, this is your lazy friend. This is your lazy friend who neither moves backwards nor towards you. All right, he stays fixed at a point. This becomes your lazy point. This becomes your lazy point. The maximum element is your lazy point. Now, as this analogy suggests, always the smaller elements, that means you, should move towards your lazy friend. You should move towards your lazy friend. So how many moves would 2 take to move towards the lazy friend? To make 2 reach 3, a plus 1 move is required. To make 1 reach 3, a plus 2 move is required. So the total number of moves would be 3. 1 plus 1 move and plus 2 moves. So it would be taking 3 moves. 3 moves in this case. Fine. This becomes the lazy point. Now, coming to the case when you can only decrement. Once again, if I decrement this further, the graph of this would be 1, 2, 3. Right? 1, 2, 3. If I decrement this further, the graph would become something like 1, 2, 3. If I decrement this further, the graph would become this way. That means the distance is like, it's getting more disbalanced than what it was previously. It's same as moving backwards. Right? You're decrementing, which is increasing the distance. All right. So this is wrong. You shouldn't be decrementing the minimum element. That would disbalance the array further. So when you cannot decrement the minimum element, and you can only decrement something, that means you cannot modify this element. This becomes the lazy element. It won't move. Now, uh, you should move towards your lazy friend. That means to make 2 to 1, you should decrement by 1. To make 3 to reach 1, you should decrement by 2. That means you would take total 3 moves, right? You would take a total of 3 moves. Fine. What if you can do both? If you can do both, that means this is the current graph. You can just do something like moving equidistant. You can move equidistant. All right. In this case, the median becomes the lazy element. The median becomes the lazy element, because if you increase median or decrease median, the graph would look something like this or something like this, which is disbalanced. All right. So in case of both, you can both increment as well as decrement. How about you move this to 2 by incrementing 1, and by decrementing this by 1, you move this to 2. So both become 2 within 2 moves. So this is how you pick optimal moves. You would consider a lazy element so that anything doesn't get more maximized. All right. If somehow, let me tell you, this is the graph, and if you had to only increment, if you increment the maximum element, this would happen, which is something you don't want. All right. This is something you don't want. All right. And if you decrement something which is already the minimum, this would happen. This also is not something which is optimal or expected. All right. So this whole logic is depending on picking the lazy element. Okay. So let's code this up. My bad. Yeah. All right. So in case of only decrement, the minimum element would be the lazy element. So lazy equal to, and you would be iterating over the array. Initially moves is 0, moves plus equal to x minus the lazy element. Okay. And absolute difference also, because moves cannot be negative. Actually, we don't need absolute because we are subtracting the minimum element, so there's no way uh, it could go negative. And if you just return moves, okay. So if I run this, it should be printing to make 2 as 1, it should take 1 move. To make 3 as 1, it should take 2 moves. So it should be printing 3. Yeah, it prints 3. And if you are asked to only increment the lazy element would become the max element, because obviously you won't increase the maximum, right? You won't increase the global maximum. So in this case also it should print 3 only. So once again it prints, no wait. This time it should be lazy minus 6. Better keep it maximum forever. Sorry, absolute forever, because yeah, it should print 3. And in case of both increment and decrement, it would become how much? This should be the median, right? The median. To find the median, you need to sort. All right. After sorting, you would do median should be AR out of n by 2. All right. So in case of both increment and decrement, what's wrong here? Okay, let's run this to find what's the error. In case of both increment and decrement, you would be finding the median, and median would be the lazy element. Let's see what happened. N was not declared, fine. Yeah, 2 moves. In 2 moves, you can make one move would be from 1 to 2, and one move would be from 3 to 2. So, yeah, that was it. You can think of more things like at most k moves or something like that. On one element, you can perform at most k moves at a time. That's nothing. You would compute modulo k and divided by k. You would add them. You would divide the moves by k and moves modulo k, and you would just add them. That's also very simple. So I hope this concept is clear. The main concept lies in picking the lazy element. Why are we picking the lazy element? If you increase the maxima, your trouble would increase, and if you decrease the minima, the trouble would increase, obviously. So that's why we are picking some something as fixed, so that it remains stagnant. So that's it for today, guys. Thank you.